So if you remember the example of the drinking water bottle as being an example of the Earth's global water system, and that the water bottle's got the lid on, so the water can't escape, it can only be stuck within the Earth system. Well, here's the last ice age. You can see time changing from around 25,000 years ago, or kiloyears, down to about 10,000 kiloyears. So there you are. And you can see the ice extent is greatest in the ice age, and it gets less and less and less. And that ice will be locking up some of the water that was previously in the Earth system. It can't be transported around anymore in the Earth's climate system. And we know that water trapped as ice is going to be isotopically relatively negative, which means that the ocean water where it came from in the beginning will be isotopically relatively more positive, have more of the heavier isotopes in it during the ice age, because the lighter isotopes are trapped in the ice. So this means we can use ocean cores to look at past climates and past environments as well. So if we take shells of animals that have grown in the oceans in the past, we measure the isotope composition, and it's taken those isotopes from the ocean water, we can say something about past oceans, past climates, maybe past ocean circulation. And I have colleagues that spend lots of times on boats such as this, and you can see the huge drill rig on top of the boat, and it goes around the oceans, taking ocean cores, drilling to huge depths to get records of past climate and environmental change. This is a map of just some cores. This is from the ocean drilling program that went until 2003. It's still ongoing. There's many more cores than this. You can see just some examples of where these cores have been taken to actually understand past environmental change. So here's an example from off North Island, New Zealand. It's a 10-meter core. So the top is here, and we're going back in time in this direction. And when you get to the bottom of that core, then the core continues here, and it goes back in time in that direction, all the way down to the oldest part of the core, which stops somewhere around about here. And all this light grey material that you can see in the core is the remains of fossils that can be analysed for the oxygen isotope composition. And one of the good things about working in regions where there's volcanoes nearby is that the ash that comes from the volcanoes can get trapped in these ocean cores as well, and that's these black layers. So here's an ash layer here, another one here, and here. There's plenty of them. And if we know the time of the volcanic eruption, or we can date the volcanic ash, then we know the time in the past. And we can then get an age for the fossils that contain the isotopes and a past environmental record. And scientists use these things called foraminifera. And here's an example of the different types of species. And these are dissolved and analysed for the oxygen in their carbonate content. So we extract the oxygen isotopes from the calcium carbonate from the shells which these animals build, and it represents something to do with the ocean water in which they were living at the time. So this is a really scary slide, and it's a quite technical slide from a research textbook, and I'm going to explain it. I've shown it because there's a couple of things that are important to know when we start talking about the oxygen isotopes when they're in calcium carbonate. So calcium carbonate is CaCO3, and we're measuring this oxygen, which was originally in the water, but it's now been converted into the oxygen in the shell material, the calcium carbonate. So the first thing to point out is that when we start working with calcium carbonate, our standard is different. We're now working with VPDB, which is the PD belemnite. It's a fossil which scientists decided many years ago to be the standard for carbonate analyses. And you'll see the numbers on the right-hand side are very different to the numbers on the left-hand side, which is the equivalent in the VSMO, which is what we've been using up to now for water samples. So you have to take care with units, and you can't just switch between water numbers on the left-hand side and carbonate numbers on the right-hand side. They have different units. The other thing I want to point out in this graph is that when you go from water here and you form calcium carbonate, which is that line here, the isotopic composition changes. It goes from a relatively light value in the water to a relatively heavier or more positive value in the carbonate. So there's a fractionation process again. And the third thing is that you see there's a temperature relationship on these lines. So the composition of the carbonate will vary depending on the temperature. So at 10 degrees, it would have a composition that's here, but at 20 degrees, it would have a composition that's slightly more negative. So maybe we can get records of past temperature from the composition of the oxygen 18 in carbonate from shells that are formed in the past. And so here's an example of an ocean core climate record using isotopes. On this graph, time now starts on the right-hand corner. So this is us today at 0, and we're now going back millions of years. One of the advantages of ocean cores is that we can go back further in time than we can for ice cores. So a long ice core record would probably only cover up to about here, just the top part of the record. The disadvantage of ocean cores is that we don't have very high resolution records. Ocean sediments get mixed up and bioturbated and compressed as they're laid down on the ocean floor. But we still see the change from the current climate here, which is a warm period, down into a glacial, the previous warm period, a glacial, previous warm period, backwards and forwards through time. And we see that these vary very regularly in the recent period over a time period of 100,000 years. This is due to changes in the Earth's orbit relative to the Sun. And we also see variability earlier on in history, about 2 million years ago, where this cyclicity was 41,000 years. So ocean sediments provide this unique evidence that goes back, in this case, over 5 million years of the transition from a warmer climate here, about 3 million years ago, and then the transition into the Quaternary climate change and the Ice Age world that we live in today. But it's relatively low resolution, and it depends on us understanding how the isotopes get incorporated into the foraminifera, and there are different species that may live in different parts of the ocean, and they all have a temperature dependency on their isotopic composition, and their isotopic composition may also vary with what the ocean comprises as well. So it's a complicated archive. So now you know something about the oxygen isotopes in ocean cores and also in ice cores. What do you think are the relative advantages and disadvantages of working with an ocean core compared to an ice core?